All right, so today we're going to look at some properties of the free electron gas. We have a free electron gas as we discussed in the previous lecture, and today we're going to use a model called the Sommerfeld model. And the Sommerfeld expansion to derive some properties of this free electron gas. In our previous discussion on phonons, we derived analogous properties of phonons. The phonons were also spread out in the reciprocal space. They had particular wave vectors, particular frequencies. They belong to different branches in the dispersion relationship. We derived not only the dispersion relationships but the total energy content in the phonons, and we derived, for example, the specific heat capacity associated with the phonons. Now we would like to do an analogous treatment with these free electrons. These free electrons are now delocalized, they are everywhere inside the solid, and this model, by the way, is very relevant for alkali metals in group 1 of the periodic table and group 2 of the periodic table, which are called the alkaline earths. The model does, however, break down for other elements in the periodic table, such as transition metals and rare earths. However, this is our first introduction to looking at properties of electrons. And we've also have looked at some relationships. For example, we do know that if we have energy here and we look at the density of states for the electrons in 3D, we have a relationship which changes as the square root of energy in 3D. That's what happens in 3D. So this dispersion relationship goes as the square root of energy. We also do know that we were able to define a Fermi-Dirac distribution function which tells us the probability of occupancy of certain energy states, and this is the Fermi-Dirac distribution at 0 kelvins. And as the temperature varies, this sharp transition smoothens out. Another interesting subtle effect that does happen that we will consider today is that the chemical potential also varies as the temperature changes. So at room temp at 0 kelvins, the Fermi energy equals the chemical potential. So the chemical potential at 0 kelvins is called the Fermi energy. However, as the temperature changes, this chemical potential also changes a bit. So not only does this sharp step function smoothen out as the temperature goes beyond 0 kelvins, you also see a slight shifting of the chemical potential, and this is what we're going to derive today. Now, in order to look at all of these properties, there is a model that was proposed by Sommerfeld back in the 20th century, around I think 1910 to 1920s, and the model goes as follows. The model really looks at describing the properties of free electrons in terms of an integral. For example, if I form this integral dE F E, and I have some property, some variable multiplied with the Fermi-Dirac distribution function. For example, if I have dE, just dE, the density of states, what should this integral be? This integral should be some number, the number of electrons inside the system. If I take dE, FE, dE, E. Then what should this be equal to? This should equal the total energy inside the system. So what is really happening is that if we would like to find out different quantities, we have an integral over energy from 0 to infinity, and we multiply a Fermi-Dirac distribution function, which, as you all recall, is given by 1 over e raised to power e minus mu over kBt plus 1. We multiply this factor with some other variable to get some quantity of interest, right? So this is the general form for calculating a certain variable which of interest for this electronic system. All right. Now what the Sommerfeld model does, it generalizes this. So the Sommerfeld model defines an integral I, which is given by dE, Fe, and some other variable, and that variable is called gamma prime E, from 0 to infinity, where gamma prime E is the derivative of gamma with respect to the energy, and our property of interest, this gamma at 0 energy, is given by probably 0. So this is the Sommerfeld integral. All right. Now, first of all, we would like to solve this integral, and then we would put gamma prime E equal to D. That will yield the total number of electrons. Then we'll put in another calculation, we can put gamma prime E equals to the density of states multiplied by the energy, and we'll get the total energy for the electrons. But let's come up with a general formula for calculating the Sommerfeld integral. Got it? All right. So how can we solve this integral? How do we solve this integral? बताएं? कैसे सॉल्व कर सकते हैं इस इंटीग्रल को? What's your best guess? By parts, right? So my I equals DE FE. So let me take F as the first variable, FE from 0 to infinity. Remember, F is my Fermi-Dirac distribution function minus 0 to infinity dE FE followed by the integral of gamma. Correct? All right, so let's look at this first term. So the first term, f at infinity is 0 and f at 0 is 1. That's what the Fermi-Dirac distribution function is. If your energy is 0, the likelihood of occupancy of that state is maximal. So this is minus 1. Excuse me. So when this is infinity, f goes to 0, and when this is 0, gamma goes to 0. So this is 0. Now I'm left with minus 0 to infinity dE Fe gamma E. Alright. So if I now look at gamma E, let's expand this gamma about the chemical potential. So this gamma E equals gamma at the chemical potential, which of course has dimensions of energy, plus the derivative of gamma with respect to energy computed at the chemical potential, E minus mu, plus 1/2 the double derivative of gamma computed at the chemical potential, E minus mu square, plus higher order terms. Correct? Now I insert this expansion for the gamma function into the integral. My integral turns out to be minus 0 to infinity dE Fe gamma mu minus dE Fe E minus mu. Let me write this as gamma prime computed at mu minus 1/2 dE by the way, this if I solve by parts, this f should really be shouldn't this be a derivative? This should be a derivative, right? And other terms. Is this making sense? Now if I look at the first term in this Sommerfeld integral, this is a constant. This is the variable gamma computed at the chemical potential, which is some constant, because the chemical potential is some constant, right? So this will give me minus gamma mu dE F prime E 0 to infinity minus gamma prime mu dE F prime E minus mu minus 1/2 the double derivative of gamma dE F prime E minus mu whole square. Now what do you think this first term would be? This is a Fermi-Dirac distribution function, and this is the derivative of the Fermi-Dirac distribution function. So if you plot the Fermi-Dirac distribution function and take its, so it's a probability distribution function. So if I take the derivative of this, I'll get a Dirac delta function pointing in the negative direction at E equals mu, and the area under that Dirac delta function will be 1. So this thing will give me minus 1. Remember that if I were to plot the Dirac delta function, the Fermi-Dirac distribution function, this is what it looks like. This is what the Fermi-Dirac distribution function looks like. At mu, this is a unit step function, it's 1 over here and drops to 0. This is my f. If I were to plot f prime, which is the derivative of this, I'll just get a Dirac delta function over here. Correct? Since the area under this curve must be 1, the area under this Dirac delta function, the magnitude of this Dirac delta function is -1. Okay? जी, क्योंकि पॉजिटिव से जीरो जा रहा है ना, तो इट्स अ negative pointing Dirac delta function. So this term over here is the integral of this function, which is the area under this curve, which is -1. So my I turns out to be plus mu computed at the chemical potential minus mu prime mu 0 to infinity dE f prime e minus mu minus 1/2 the double derivative of mu dE f prime e minus mu squared. All right. So in order to compute the second term in the integral and the third term in the integral, I can come up with an explicit mathematical form for the Fermi-Dirac distribution function. So the Fermi-Dirac distribution function is written over there in yellow. So I can take the derivative of this term. So what I could do, I could make e minus mu x my Fermi-Dirac distribution function can be written as a function of x as 1 over e beta x plus 1, where beta is 1 over kbt. So if I were to take the derivative of this is really e beta x plus 1 minus 1. If I were to take the derivative of f prime e, which is same as f prime x, this is going to be equal to minus 1 over e beta x plus 1 square beta e beta x, isn't it so? So this will become minus 1 over kbt 1 over e beta x over 2 plus e minus beta x over 2 squared. This will be minus 1 over kbt secant h square beta x over 2. Correct? And I can put x, replace e minus mu back into x, I'll get the form for the derivative. Now this is the inverse of the cosine function, a hyperbolic function. Right? What does the hyperbolic function look like? So if I were to plot some cosine of something a x, this is my 0. What does a cosine function look like? Is it even or odd? It's even, right? It has this form. It's an even function because it's defined as e raised to power x plus e raised to power minus x over 2. That's how a cosine function is defined. So this is an even function. The square is also an even function, and the inverse of the square is also an even function. So right here I have an even function. And right here I have an odd function in e or x. Now this integral is from 0 to infinity, but f prime only exists in the vicinity of the chemical potential. So I can extend this to minus infinity. So I can take the integral of an odd function from minus infinity to plus infinity, and that will be 0. So I'm going to be left only with this term over here. So I have now found out what my I is going to look like. My I will be the gamma, the variable, the unknown variable computed at the chemical potential, minus 1/2 the double derivative of mu. Let me replace the variable e by x, 0 to infinity dx. This is x squared, e minus mu squared is x squared, and f prime is given by this, so I'll put 1/2 here, kbt secant h square beta x over 2. This integral can be solved. Okay, this is a standard integral, it can be solved. This will be some numerical factor over here, some numerical factor. But the key is that the integral that I aim to solve, the Sommerfeld integral, is the variable gamma computed at the chemical potential plus 1 over 2 kBt, the double derivative of gamma computed at the chemical potential, and some numerical factor. So you can look up what this numerical factor looks like. It's something pi square over 6, something of that kind. Higher orders में नहीं जा रहे, वो homework में जाएंगे. So overall, my I the Sommerfeld integral I, which I would like to write down again, the integral over E of Fe gamma prime E, this is equal to gamma computed at the chemical potential plus pi square over 6 kBt goes into the numerator and the double derivative of mu. So this is our Sommerfeld integral. Now let's use this Sommerfeld integral to compute a few things. First of all, let's see whether we can employ the Sommerfeld integral to find out how the chemical potential itself depends upon the temperature. Let's see if we are able to find this out. The chemical potential has a weak dependence on the temperature itself. Let's see if we are able to employ the Sommerfeld integral for this purpose. For this purpose, what we would like to do is we would like to solve the integral dE Fe dE. Right? This will of course give us the total number of electrons inside the system at any temperature whatsoever. At any temperature. If we are changing the temperature of a solid of fixed volume, we're not changing the number density of electrons. So this expression will be valid for any temperature, and it's going to be valid for 0 kelvins as well. For 0 kelvins, this F becomes equal to 1 for temperatures less than EF, and you take the integral from 0 to EF. So this number has to be equal to n, and this integral has to be independent of temperature, because the number of electrons doesn't change with temperature. But now through this argument, through this logical argument, we would like to find out how does the chemical potential change with the density of states. And the chemical potential is really appearing in the formula for the Fermi-Dirac distribution function. Okay, so if I compare this n with I, the identification that I'm able to make is that my gamma variable is such that its derivative is equal to the density of states. So if I compare these expressions, and in I, if I set gamma prime equal to the density of states, then I can just use this formula over here and find out the integral. Isn't it true? So if I make this comparison between this I and this n, there I can identify that this term dE must equal gamma prime, and then I use this formula over here. Gamma double prime will become the first derivative of the density of states, right? So that's what I would like to do now. So I can simply employ the formula, the Sommerfeld expansion. My n will become equal to gamma at mu plus pi square 6 kBT whole square, the double derivative of mu. Now what is gamma at mu of mu? So the gamma of mu is the integral of this. Okay, so this is my gamma prime. What is my gamma? My gamma is the integral of dE. So I change this variable to E prime, and I integrate from 0 to E to obtain gamma. So if my gamma prime is the density of states, my gamma will be the integral of the density of states. And gamma prime at some energy E will be equal to this. Since I need a double derivative of gamma with respect to energy, I need to compute gamma E. So my gamma E is going to be, I know that my dE is really C E prime 1/2, right? Some constant C, dE prime 0 to E. This becomes 0, E 3 by 2 and a 2 by 3 here. This is my gamma at E. Okay. So I have computed this term over here. Gamma at the chemical potential would simply be obtained by replacing E with the chemical potential. I now also need the double derivative of this term. So how do I find out the double derivative? I just take the derivative of the density of states. So I have found this term, right? This term has been computed. Now I need to focus my attention on the second term. The second term has a double derivative of gamma, but the first derivative is already known, so I take the derivative again. So if I were to take the derivative again, let's make this equation number 1. At the end, I'm going to insert all my computations into equation number 1. The second derivative of gamma is going to be given by C E 1/2 minus 1, which is minus 1/2, right? So now I insert this computation in here, and I insert this computation in here. And I know what n is because I can do a computation at 0 kelvins as well. So my n is gamma computed at mu, but this is my gamma. So this term at mu becomes 2 over 3 c mu raised power 3 by 2 plus the second term pi square over 6 kBt whole squared. Now I need to take the double derivative, which is 1/2 c mu raised power minus 1/2. Correct? But this n is नमता साहब कैसे सर आवाज़ ज़रा ऊंची कर दे बस. But this n is also equal to the number of electrons at 0 kelvins, which will just be this integral from 0 to EF, where F is just 1. So this will also be equal to C0 to EF dE prime E prime raised by 1/2, which equals C EF 3 by 2, 2 by 3. ठीक है, एक मिनट, अब ठीक, अब बेहतर है, ठीक है, शुक्रिया शुक्रिया. Now let's do some fortuitous calculations. So let's remove this C. Let me remove this 2 by 3 as well. And I multiply this with 3 by 2. And let me divide both sides by EF raised power 3 by 2. So I make this 1. This will become mu over EF 3 by 2 plus pi square over 8 kb t square mu minus half e raised per f 3 by 2 equals 1. Right, so this makes sense. So 1 equals mu over EF 3 by 2 plus pi square over 8 kb t whole square is half mu 3 by 2. This equals 1 EF 3 by 2 1 plus pi square over 8 kbt whole square over mu. किधर? All right. So what? Okay. एक मिनट. So this is correct up till here. So I have just taken this as common, this becomes 1. So this is already here. So this is what I have over here. So what does this show? So I could kind of rephrase this as pi square over 8 kBt over mu squared minus 1, right? Now this mu is the chemical potential, which is now slightly deviated from the Fermi energy, correct? Now the Fermi energy is much higher, the Fermi temperature is much higher than the ordinary temperature, the ambient temperature of the bath. So this mu will still be close to the Fermi energy, and the associated Fermi temperature is much higher than the bath temperature. So this is a very small term. So I can employ the binomial expansion over here. So this will become approximately, after the application of the binomial expansion, 1 minus pi square over 8 kBt over. Now I can express this mu over here. Since it's a square, this mu is close to EF. It's not EF, but it's close to EF. So this mu is really EF plus some delta. So if delta is small, I can, and we have a square over here, I can replace this mu as a first order approximation to be equal to EF. So, and you can do this explicitly as well. Just expand mu as EF plus delta. It's in the denominator, take the square, apply the binomial expansion, you'll get a term which is of second order of delta, which is even smaller. So I can replace this mu with an EF as an approximation. So this will become EF. Now EF is really kBt, the Fermi temperature, square. All right. So all in all, what I obtain is the following: mu over EF is 1 minus pi square over 8 T over Tf squared. All of this now raised to power 2 over 3. This means that my mu equals EF 1 minus, I again apply the binomial expansion. I'll get 1 minus pi square over 12 T over Tf. So this power just becomes 2 over 3. So this becomes 1 over 12. So this really shows the dependence of the chemical potential on the temperature to a first order approximation. This T is really small as compared to Tf. This Tf could be thousands of kelvins, as we know, because the Fermi energy is 5 electron volts, 6 electron volts, 4 electron volts, these large numbers. The Fermi temperature is consequently much higher than the room temperature or the ambient temperature at which this experiment is being performed. So this means that the deviation of mu from EF as the temperature goes up is very minute. But there is a weak dependence on the Fermi temperature on the temperature. If I were to plot this, T, mu, the chemical potential at 0 kelvins, of course it's equal to EF. But it doesn't deviate even a tiny bit from EF as the temperature remains modest in the intermediate regime. Only at very high temperatures, when T approaches TF, most of the solids will melt before that. Does the temperature, at these high temperature regimes, would there be slight deviation of the chemical potential from the Fermi energy? So in the Fermi-Dirac distribution function, this position, the Fermi-Dirac distribution function, this function here has only very slight dependence on the temperature. This mu only slightly depends upon the temperature. And at very large temperatures, would this threshold, this precipice between function being 1 and 0 is going to slightly shift downwards. Okay? So this is one application of the idea of the Sommerfeld calculation. Yes, please.
So why are we able to equate I and N here? Like, is it just like using
So this is I. Any integral of this kind, we call it I, equals this to second order in the temperature. Okay? Now we want to calculate N. So N luckily is already expressed in a form isomorphic to this integral. We only need to make an identification that this derivative of the unknown variable gamma must equal the density of states.
But it could be, it still could be anything different from it as well. Like, or does it need to be equal to that derivative?
So if you want to calculate this, so this is the integral we would like to calculate. Yeah. A task is made easier because we've already come up with a solution for an integral that is isomorphic to this. It's analogous to this. So we know that the solution to this integral is given by this. So we just compare our desired integral to the Sommerfeld integral and directly use the solution to the Sommerfeld integral. That's what we're doing. Okay? Now let's look at another example. Suppose I want to calculate the total energy for the electrons inside the system. Yes, please. क्योंकि देखो, this TF is much larger than T. This could be, say, 3000 kelvins. This is at room temperature, this is only 300 kelvins. So this is 1 over 10. Squared is 1 over 100. This 1%. So 1%, so you're doing a 1% change in 1, which is 0.01. So the change in EF is only 1%, even at room temperatures. However, if the temperature becomes large, if T becomes equal to TF, then you might get large deviations, significant deviations from the Fermi energy. Okay, so the dependence is very small because T is being divided by TF and TF is much larger than T. Remember that solids have to melt. The bonds have to break if we heat the solid. So this calculation would then no longer apply if we do not have a free gas of electrons. So these calculations are only for free electrons. These electrons are not interacting with one another and they're not seeing any band potential. They're not seeing the periodic potential of the ions. This is valid only in the Jellier model, in which we have a homogeneous soup of positive background ions, which is homogeneous, which is not studied periodically. This is just homogeneous soup, like a soup. Okay, so this is a free electron model that we are still delving into. Now, if I were to calculate my next task, I want to calculate the specific heat capacity for these electrons. We've already done this calculation for phonons. Now we would like to do it for the free electrons inside the solid. So I would like to calculate the total energy. So what kind of integral should I write? Can you please, anyone, come to the blackboard and write down the integral at arbitrary temperatures? So it's simply the integral that we've already written over here, the second integral on this blackboard at the top. The only thing that, so how do we solve this integral? We don't have to do the grind over and over again. We make an identification of u with I. So u will match I. So this is the u we would like to solve. But we know how to solve this. So what identification do we make? We want D into E. The density of states into E to be equal to gamma prime. So we integrate this entire thing and get gamma, and we differentiate this entire thing and get gamma prime. Can you start this calculation, please? You need to work more with your hands. Equals EdE. Correct? So this is some C, E is about 3 by 2. Half power half plus 1. So from here I can calculate two things. I can calculate the integral, which will yield gamma E, which is C e raised to power 5 by 2, 2 by 5. And I can calculate the second derivative of gamma, which is just the single derivative of this thing, gamma double prime E equals 3 by 2 C E 1/2. Right? So now I insert these expressions into my Sommerfeld integral while replacing E with mu, with the chemical potential. So my u would become gamma at mu, which is 2 over 5 C mu raised to power 5 by 2 plus pi square over 6 kb t square, and the double derivative of gamma, which now is 3 by 2 C E 1 mu raised to power 1/2. Okay, so I would like to take this as a common 1 plus pi square by 6 kb t whole square 3 by 2 C 1/2 multiplied by 5 over 2 C mu 5 by 2. This will help me cancel out the C. So 3 5s are 15. This will be 2. 5 over 8. 5 over 8 pi square kBT square mu square over mu square. Okay, right? So far so good. Once again we observe that if I were to replace this mu with kBTF exactly using the same arguments, I can do that. So this mu, because mu has a very weak dependence on the temperature, I can replace this with T over Tf. I still get this dependence on the temperature, which is still a small factor. What about this term over here? Can you make an identification? What do you think this term should be equal to? Just by looking at the expression for the U at any temperature greater than 0, what should this term be equal to? Just by looking at, just by the appearance of it. The energy? This is the total energy, not the Fermi energy. This is the total energy. So if I were to take in this expression, if I were to take this equal to 1, then I integrate this, I'll get the total energy. So, and I can take this equal to 1 when this is EF and I'm at 0 kelvins. So this term over here, if I were to replace mu with and at 0 Kelvin, mu equals EF. So this term is really the total energy at 0 kelvins. Okay, so I'll get U at some temperature is the total energy at 0 kelvins plus 1 plus 5 pi square over 8 T over Tf whole square. So this gives me the total energy. Once again, I've used the Sommerfeld expansion to find out the total energy inside the solid due to electrons, due to free electrons. That's the energy. Now what about the heat capacity? So I differentiate this. So what will the heat capacity be proportional to as a function of temperature? Temperature, just the temperature. So now inside this solid, you have these free electrons, therefore it's a conductor. So you're looking at a conductor such as a metal, a normal metal, and you have this temperature dependence on the heat capacity. But inside the same solid, you also have phonons. And the phonons are coming from the ionic vibrations. And they will contribute to the heat capacity as well. So you are putting energy into the system. Some of this is going to raise the temperature of the phonons, and some of it is going to raise the temperature of the electrons. So the overall heat capacity for this solid, which by the way is non-magnetic at the moment. So this is a conducting solid we're talking about. So there is a heat capacity associated with the electrons that has a temperature dependence, linear temperature dependence. What about the dependence of the heat capacity on the temperature for phonons? What does that look like in 3D? T cube, it's the cube of the temperature. So I have some dependence on the temperature plus some dependence on the temperature due to phonons. So this term is due to phonons, this is the phononic heat capacity, and this is the electronic heat capacity. And this term, of course, will depend upon Tf. The Tf depends upon the Fermi energy. And the Fermi energy, we know this depends upon the mass of the electron, right? Remember our formulas. For free electrons, kBTF is the energy. This is equal to kBTF, this is the temperature, and this must equal to the energy of the free electron, which is h bar square m square h bar square k square kf square in this case over 2m. Now here m is the mass of the electron, the mass of the free electron. So this Tf does depend upon the mass of the electron, right? So the heat capacity, this gamma, will depend explicitly on the mass of the electron, correct? Because we have Tf over here. Tf is just another way of saying the Fermi energy. This equals the Fermi energy, correct? So Tf, this factor here, gamma, is sometimes called the Sommerfeld factor, does depend upon the mass of the electron. This is the overall heat capacity for a solid. Now inside this solid, if I were to do an experiment, now experiments are the final arbiter of physics. Nothing else decides what is correct, what is incorrect. The final arbiter of truth is only experiments. So if one were to do an experiment, finding out the heat capacity of the solid. Now if one were to do an experiment with an insulator, you wouldn't get the electronic term because there are no free electrons available. So you can focus your attention on the phonons. If one were to do, however, an experiment with a conductor, so you'll have both the phononic term and the electronic term because you have free electrons inside the system. By the way, the system is still non-magnetic because we're not talking about quantized spin oscillations, which are called magnons. That's beyond the ambit of this course. So if I were to plot CV versus temperature, in fact, if I were to plot CV divided by temperature versus temperature squared, what kind of graph should I get theoretically? Linear. You should get a straight line, right, just by looking at the expression over there. So this intercept, what is this intercept? That's gamma. That's the gamma that I've written over there. So for most alkaline metals, from this gamma you can calculate the mass of the electron inside the solid. These temperatures, by the way, are very low, right? These temperatures are of the order of millikelvins or microkelvins or kelvins, not more than that. Because from the expressions, the T cube expression is only valid for low temperatures, as you know. For higher temperatures, you have to use the entire Debye interpolation curve. So this formula is only valid for low temperatures, at which real experiments, real meaningful experiments in physics take place, of the order of millikelvins or kelvins. Now this gamma can give you directly the mass of the electron, which in this sense is coming out from an experiment. So you can find out the mass of the electron through this experiment. So most solids, most metals which belong to the group 1 or group 2, the alkali metals and the alkaline earth metals, they kind of have this a value of gamma that does give you the proper mass of the electron. But if you do perform this experiment, say for nickel or gold or transition metals, iron, this factor, this gamma changes altogether. So the mass of the electron for such systems is not equal to the real mass of the electron. So those systems are called heavy fermionic systems. These are heavy fermionic systems, and they're heavy because the electrons in those systems are interacting with one another. In these alkaline metals, the electrons that are conduction electrons are only s electrons or p electrons. But if you have d electrons or f orbital electrons, then you will have a heavy fermionic system. Heavy fermionic system is a system in which electrons are strongly interacting with one another, and you get all kinds of cooperative electronic effects. Okay.
So इलेक्ट्रॉन का mass बढ़ जाने का मतलब क्या है? अभी वो तो constant नहीं होता।
नहीं. Electron, this is an excitation. Electron, in this quantum field model, the electron can have a mass which is substantially different from the rest mass of an electron. Relativistic effects भी होते हैं, लेकिन band structure की वजह से भी masses change होते हैं. The effective mass is inversely proportional to the group velocity. Okay, so the group velocity changes, the mass of the electron changes, and at certain group velocity, certain values of k, the mass of the electron can change. It can also be negative, which means you apply an electric field in one direction and the electron starts moving in the other direction. So the mass is a very fitful concept in condensed matter physics. It's not the same inertial mass that we are used to. Okay. Now, the third example I would like to give from the Sommerfeld expansion deals with magnetism. Yes. Sorry? Slope variation. The slope here A would depend upon the ionic structure. It will depend upon what kind of crystal structure do you have. So that we've already derived from when we were talking about the phonons. And the slope can change. So they all have the same gamma, but different slopes because they have different A's. Now the third example I would like to give is of one kind of magnetism, and that is called polyparamagnetism. Inside, and it's valid for solids again, which have free electrons like alkaline metals or alkali earth metals, sodium, potassium, and so on. Now polyparamagnetism arises because, first of all, do you know the meaning of paramagnetism? What is paramagnetism? Every physicist should know what paramagnetism and these basic concepts of magnetism. क्या होती है paramagnetism? So it's a weak magnetic effect. You apply a magnetic field so you have a solid and you apply a magnetic field H, say in a particular direction, and a magnetization develops inside this solid parallel to the field M. This is called paramagnetism. If magnetization develops opposite to the applied field, it's called diamagnetism. So for linear solids, linear isotropic homogeneous materials, this M is proportional to H. It is given by a constant called the paramagnetic susceptibility. And generally put a minus sign as well, or a positive sign, and deduce that chi is negative for a paramagnetic material because M is opposite to H. So this is paramagnetism. Okay, so whenever you have free electrons, you have this kind of paramagnetism, which is called polyparamagnetism. But you will also have diamagnetism when you have free electrons. So there will be two competing effects, and whatever wins is a case in point. You need to understand which effect wins. But diamagnetism is due to the lens's effect really. So if you apply a magnetic field, the electrons will start rotating in an orbital motion to produce a magnetic field that's opposite to the applied field. So there is always some diamagnetism for bound electrons and free electrons. But free electrons do give paramagnetism as well. So what we would like to see now, how does this model, this Sommerfeld model, describe polyparamagnetism? Now if I place, we know that every electron that we're talking about, so far this is our first kind of introduction to the spin of an electron. The electrons have spin as well. These free electrons, the giant soup of spins as well, pointing in random directions if there is no magnetic field. So the magnetic field will orient these spins preferentially in one direction. So in my modern physics class and in so many other different kinds of courses, I've kind of talked a lot about this. So if I have an electron, it has a magnetic moment mu b, to keep things simple, which is the Bohr magneton. From atomic physics, we know that mu b is a constant which is Eh bar over 2 times the mass of the electron. So this is a Bohr magneton. This is a small unit of magnetism, small unit of magnetic moment. So whenever I place an electron inside a magnetic field, it can either align with the field or disalign with the field. So these are two eigenstates that are formed. So applying a magnetic field quantum mechanically applies a Hamiltonian, which is given by minus mu b b. If the field is applied along the z direction, I will have the Pauli z operator. So this Hamiltonian is applied when I put an electron inside a spin. Just putting an electron, any spin, any magnetic moment inside a magnetic field is going to apply this Hamiltonian, which means the eigenvalues for this Hamiltonian will be mu b, b, eigenvalues for sigma z, which are +1 and -1. So I'll get these two energy states. Two kinds of energies, mu b, b. So spins that are parallel will have energy minus mu b, b, and spins which are anti-parallel will have a higher energy. Now if you have your solid with free electrons in it and it's in zero field environment, which is practically very hard, but just assume for a minute it's in zero magnetic field, there will be no preference for the spins to be aligned or anti-aligned. So there will be as many on average. If you take a snapshot, these spins will be randomly aligned and there will be no magnetization of the sample. So where does this magnetization come from? This magnetization in fact is coming from tiny electrons with dipole moments pointing in different directions, but the net magnetic moment is such that the vectorial sum of these magnetic moments is nudging slightly in some preferred direction. So M, capital M, really is the vector sum of all the magnetic moments inside the solid divided by the total number of spins. This is how we define magnetization. So now if you have zero magnetic field, there is kind of no preference between spin up and spin down. So if I were to plot, so now I'm going to plot a density of states diagram, E, dE. Okay, let's plot. So this is how you generally plot density of states. So I would now like to plot this diagram in a different fashion. I put E here. Oh no, just let's. I put E here. DE. Let me put this. I put E here. I put energy here and dE here. Generally, you put E here and dE here. So now for electrons, so what I have, I have this soup of electrons. They have a density of states which is which has a square root relationship. Where have I plotted this? Like this, okay? So this is my density of states diagram. Now this is valid for spin up electrons as well as for spin down electrons. The same density of states, because I have not yet applied any magnetic field. So the energies are the same for spin up and spin down. So I can plot a diagram. This is the density of states. So suppose this diagram, and this is my, everything is at 0 Kelvin. So this is my Fermi energy here, equal to the chemical potential. So suppose this is my Fermi energy. So all the electron states up till the Fermi energy are populated. But I can also draw a similar diagram for spin down states. It will have the same density of states. So these two kind of laws will be mirror images of one another. So one corresponds to spin up, the other corresponds to spin down. So I have drawn this density of states diagram so as to differentiate between these two kinds of spin manifolds. Okay? And both of these spin manifolds are populated up till the Fermi energy. Now what if I switch on a magnetic field? What happens? The energy of the spins that are aligned with the field, suppose the field is in the upward direction, the entire energy manifold, this energy manifold is going to lower its energy, isn't it? Because of this minus mu BB. So each electron, remember that electrons are filling these energy levels, right? Whatever the energy levels are, it's electrons all the way from the bottom to the ceiling, which is the Fermi energy. So electrons are filling this manifold, and the opposite spin electrons are filling this manifold. Now when I apply a magnetic field, this entire, so far it's not a band, but let me use this word very loosely. This band of spin up electrons is going to be lowered, and this band of spin down electrons which have anti-line, their energy is going to raise. So all of a sudden what happens on an instantaneous kind of time scale, if this were my Fermi energy before the application of a magnetic field, this entire band is going to shift up a little bit. Sorry, this is going to this is parallel to the field, so it's going to shift down. Sorry, so this is parallel to the field. It's going to shift down. This band is going to shift upwards. This band is going to shift downwards.
Starting points भी बदल रहे हैं.
अभी देखते हैं, बिल्कुल. Yes. Let's call this D, right? This is the Fermi energy and it remains where it is. So this dashed line is extrapolated to this diagram, the same line, the same level. So now what we see is that instantaneously, just imagine that this shifting of bands take place. The spin up band goes down in energy because it's preferentially aligned with the magnetic field. This spin down band goes up in energy because it's anti-aligned with the spin. Now at this, in the region or in the vicinity of the Fermi level, what we see is that there are electrons in the high energy state and there are vacant states over here. Now these electrons are inside the same medium. So if an electron is in a higher state and it sees vacant states in the vicinity of the Fermi level, then these electrons which are in this region, say, in this region, they are going to hop from this band into this band. And they're going to flip their spins. Hopping from one band to another really means flipping the spins. We still have 5 minutes left, right? Yeah. Let me know. It's fine. So electrons will leave this spin down band, will flip their spins, will leave a hole over here in this band, and after this instantaneous rearrangement of energy levels, what's going to happen is that the area under this region, which gives you the total number of spin up electrons, will be higher than the area under this region, which gives you the total number of spin down electrons. So there will be more spin up electrons than spin down electrons. So a magnetization will develop. And we can calculate this magnetization. Let me show you how to calculate this magnetization. So in order to calculate this magnetization, by the way, all this action is happening in the vicinity of the Fermi level. Everything is happening over here. Nothing is happening over here because there are no, it's jam packed over. It's a traffic jam here. All the levels are filled. Only vacant levels become available at the Fermi level. And that's where the spin hopping, the spin transversal with the spin reversal takes place at the Fermi level. So that now there are more spin up electrons. Now if you want to calculate this population difference between the two kinds of electrons, you'll get n up minus n down. So let me write down the integral for this, and you'll be able to solve it. It's another Sommerfeld kind of integral. So this will be dE d. Now spin up electrons have now a lower energy, so I will put E minus mu bb instead of E. Suppose I'm at 0 kelvins, right? So F equals 1, so I put this right. So this is the number of spin up electrons, because the energy is now lowered. So instead of dE, we now have dE minus mu bb minus dE capital dE plus mu bb at 0 kelvins. Okay, so this term over here dE, I expand this in the absence of a magnetic field, so this becomes dE at F plus partial d or partial E computed at EF with the minus sign mu bb, right? So I do a Taylor series expansion of this d, correct, minus dE d at EF I'm doing expansion about the Fermi level, d at EF plus partial d over partial E computed at EF mu bb, right? This will, now I would like you to kind of unpack this integral, right? Just unpack this integral, and then you take your delta n, which is the difference in the number of electrons. You multiply this with the magnetization of each electron, which is B. This will give you, then you divide by the total volume of the solid. This will give you the magnetization of the solid. You put this equal to chi h, where h is given by B over mu naught. B is the applied field and h is B over mu naught. Mu naught is the permeability of free space. You can calculate what chi is going to be. Chi will be independent of temperature and inversely proportional to the Fermi temperature. So please complete this calculation before we come for the next class. Hopefully tomorrow, but let's see. ठीक है, होमवर्क नंबर 5 आपने काम करना है, उसमें मैंने एक कैलकुलेशन दिया है 2D सॉलिड के लिए फोनॉन्स की. ठीक है, थैंक यू वेरी मच.